Here we go. Check your, be a good, honest grader for yourself, because this doesn't matter. It just will let you know what you need to practice. So, so number one should look something like this. Um, you can really have your forces going any way you want, but they need to add up to 7 newtons upwards. So the reason this does is because these two forces are the same, and they cancel out. This is positive 5, this is negative 5, so if you add those, you get 0. This is positive 10, this is negative 3, so you get 7 upward. Yeah, it could be any numbers. Any numbers you want. Abby, I answered your question. Yeah. As long as this is 7 more than that. Now on the quiz next class, it could be draw a diagram experiencing 4 forces, experiencing a net force of 2 newtons to the left. And if you did that, then the up and down forces, they should be the same. And the one to the left should be 2 more than the one to the right. But you could do like 3 to the left and 1 to the right, and then 4 up and 4 down. Or, there are different combinations. It could be a net force of 3 newtons downward, or a net force of 7 newtons to the right. Now the child pushing the toy car, what I'm doing is having you really play around with Newton's second law here. And if I take just force equals mass times acceleration, this is the net force. If you keep the net force the same, you can have a really big mass and little acceleration, or you can have a little mass and a big acceleration. But then you can also start tinkering with the force itself. So in the first one, if you take this formula and you increase the net force, but you keep a little mass, then what you're going to get is a big acceleration. That should make sense to most people. If you have the same mass car, but you push it harder, it's going to accelerate more. And then in this next one, what happens if you keep the force the same? So I've got the same size force, but now I've got a really big mass. That's going to make the acceleration small. So the answer is, I don't care what you do as long as you write acceleration increases, acceleration decreases. I guess if you said it goes faster and goes slower, I'd probably take that too. Because that's, what's that? Yeah, you can write it in words. You don't need the diagram. Just what I circled there is the best. Perfect. Yeah. Okay. Number 3, the action and reaction pairs. So I'm going to be picky about this. If a student's going to jump upward, the student needs to push the floor, the ground, whatever, downward. So you have to say the student pushes the floor or the surface they're standing on downward. You have to say the floor or whatever it is the student pushes downward, that pushes the student up. Now, did you say it goes down? Floor doesn't really. Technically it does, yes, but not much. But no, no, no. You're supposed to name the forces. But if you say the floor goes down, that's not saying the floor is pushed down. Just say the floor is pushed down. Because that's a force. The water rocket, the rocket pushes the water down, the water pushes the rocket up. Yes, what's your question? Yeah. Gianni? What would be different that no. So here it says in here, make sure you name the objects. So first, there are 2 objects and they push against each other. Yeah. And second, give the directions of the forces. So in the first one, the 2 objects are the student and the floor, or the student and the earth, or the student and the ground. And then you give directions. In this one, the 2 objects are the water and the rocket, and tell how they push one another. People get confused about the water rocket one. It's just, it's like me when I was standing there throwing the little golf ball one way. I pushed the golf ball to the left, it pushed me to the right. Simple as that. All right, now more complicated ones. Here are the answers. This is I'll explain how I did it, but first I'll explain how to check it. So it's 3 points, and it says include proper units. I think I'm probably not going to check the units on this because I don't know exactly how to do the points otherwise. I don't want to break it up. I don't want to make this like 3/4 of a point for the number and 1/4 for the unit. So try the right units, but if you don't have them, if you just have a 20 here, you get credit. So the force of drag is 20 newtons, the weight is 50 newtons, and the net force is either -30, or you could say 30 newtons downward. So here's how I did it. My first step is I used this. I used weight equals mass times gravity. I took the mass of 5, multiplied it by, weight equals mass times g. G and gravity are not really exactly the same thing. G is just a number 10 that we use in these problems. So 5 times 10 is 50. That's how I know the weight is 50. The next thing I did is I used F equals ma to get the net force right here. So the mass is 5, the acceleration is -6. Multiply them together and you can get the net force, -30. The last part's the trickiest. I actually did it without a formula, but then I wrote a formula down. So to me, it's just easier to say this is -30. That means the downward force has to be 30 more than the upward force. So if this is 50, this has to be 30 less. So this is 20. So that's how I did it. But you can also do it by writing a formula for net force. There are 2 ways to write a formula for net force. One is to use Newton's second law, and the next one is just to add up all the forces. So if I add up all the forces, there's drag and there's weight, but I write this as drag minus weight because weight's downward and drag's upward. So drag's positive, weight's negative. So that's the net force. And I already have the net force. It's -30. So I plug that in for this, -30, equals drag minus 50 newtons, which is the weight. So now I just solve this. If -30 equals the force minus 50, then the force has to equal 20. I just add 50 to both sides. Gianni? If you wrote -50 on here, I'd give you credit. But since it's got the arrow, I'd leave it off. But I wouldn't take off points. All right, this next one, this is 4 points. And the 4 points are for the net force of 6, and the force of friction of 4, and the mass of 2 kilograms, and the weight of 20 newtons. So 6 newtons, 4 newtons, 2 kilograms, 20 newtons. Here's how I did it. First step, I mean, you've got all these tools. You have this, which I could write as a triangle also. And then you've got this, which is just saying that I can get the net force if I add up all the forces. So I use this first because if I tried these other things, I wouldn't have enough information yet. So I could find the mass using this triangle. The mass is the weight divided by g. And the weight, so, I didn't do that first. Let me just go ahead with what I was just saying, but I'll explain how I got this in just a second. Here's the weight, 20 newtons, and g is 10, so 20 over 10 is 2. Now, does anybody know how I got that? This is the very first thing I wrote. How did I know this was 20? Because this is 20, and because this is just sitting still on the ground, so these have to be the same. So like the force pushing your butt up right now is equal to the weight of your body pushing your butt down. They're balanced. Otherwise, you'd be rising out of your chair or sinking into it. So first I got this, and then I used this triangle to get the mass. And once I plugged in the mass, then I could use Newton's second law to get the net force. It's the mass times the acceleration, which is given. So that's 6 newtons. And then once I get the net force, I can figure out this missing force here. So these cancel out. The net force is just going to be 10 minus something, and that has to equal 6. So the answer is 4. So one way to think about it is this net force. Will you all be quiet? Why don't you text one another if you're not going to pay any attention and you're not participating anyway. Then everybody else can hear and I can focus. So this net force just means the force to the right is 6 more than the force to the left. If this had been negative, that would mean the force to the left is 6 more than the force to the right. So if I know this is 6 more than that, and I know this is 10, this has got to be 4. The other way to do it is to write an algebraic equation. You can just write net force equals all the forces added together. So all the non-canceling forces are this push minus this force of friction. And then I plug in values. The net force is 6, the push is 10, and I've just got to find this. So 6 equals 10 minus F. F has to be 4. So on the actual quiz next class, expect something like this. I might mess around with, the picture is going to look like this, but I might make blanks in these other places and give you some of these numbers. But you're still going to have to use these kinds of tools. The weight equals mg, F equals ma, and you'll have to know that all the forces add up to the net force. And then on this one, it'll be the same kind of diagram, but again, I may, instead of giving you acceleration, maybe I'll give you the weight. Who knows? Actually, I won't give you the weight. Yeah, so you'd use the same equation, but you'd be plugging stuff in differently. So this will still probably be a 4.1. This will probably be a 3.1. I'm going to have 2 examples where you have to do equal and opposite action-reaction. This will be, maybe I'll ask you this. A child is pushing a toy car. The net force is accelerating the car sideways. What happens if the car accelerates more? There's faster acceleration, but the force was the same. What else changed and how? So if you have the same force, but there's faster acceleration, what about this situation changed? So would there have been more mass or less mass? Less mass. So that would look like, if I did my little thing with F equals ma, that would look like this, a big A and little m. And finally, I told you about that. And unfortunately, it adds up to 13 if anybody's superstitious.